let me ask you first. What do you guys think of span as?
All possible linear combinations.
That's the definition they give you in, that's great. That's the definition they gave you in David Ley. They call it all possible linear combinations of the vectors that are given to you. So, so if you haven't seen this notation before, this means the set of. This part before the colon tells you what everybody in the set looks like. So you can think of it, this part as being a bouncer and saying, hey, I'm gonna bounce anybody that's a guy. So you walk in the door, you're a guy, you're bounced out. So something that's not in here would be maybe something that's not a vector, right? These are combinations of vector that has to look like this. The second part of the colon tells you the restriction. So it's like there's a second bouncer and they tell you, well, under these conditions, the alpha ones and the alpha n's has to be all in the reals. Now, that would be like, you got in the door, but one of your alphas was a complex number, and they say, nope, you're out. Like, that's the restriction. So there's two bouncers, basically. And this set is a club, the little swirly things. So what span really is, it's really, we do this in math all the time. We have something called a minimal set. And you're going to see this again. You will see it in other places. You might recognize it. So the idea is like you're given a bunch of vectors. By themselves, they don't have to be a subspace. So if I have two vectors by themselves, 0, 1, 1, and 1, 1, 0 in R3, by themselves, they're not a subspace. They're just two vectors. And then you ask yourself, what else has to be in there to force this thing to be a subspace? Anybody remember the definition of subspace?
Is the zero vector.
Zero vector, right?
Multiplication.
Scalar multiplication. Yeah, that's exactly right. You're on the ball, Theo. So the idea is that of a subspace, the real thing about a subspace is that it's got this closure property that you can't get out of it. It's like geometrically, in R3, a plane would be a subspace. Once you're on that plane, everything in R2 applies. You can't get out of that. Just if you've watched Superman 2, it's like that glass. They couldn't get out of it, so that you won't want to get out of it. So you can't add yourself out of it. You can't scale or multiply yourself out of it. That's the definition of subspace, Dr. T's definition. So and it's pleasurable to work on that because it's like a mini vector space by itself. So it's like a mini little planet by itself. You don't have to worry about all your properties of vector spaces come down on it. So that's what's cool about a subspace. So then you can ask yourself, I want to stir myself up a subspace. And you throw in a couple onions, V1, V2, V3, you throw them in, and you ask yourself, well, what combination will force this thing to be a subspace? So the minimal ingredient subspace, if you had just one vector, it would be all multiples of that one vector. That would make a subspace. If you had two vectors, it'd be all linear combinations of those two vectors because you'd have to have all multiples of both because you need to not jump out of the set by scalar multiplication. And then you don't want to add out of the space. So you need one combination, one scalar multiple of V1 and one scalar multiple of V2, add them together, you can't get out. So that's why you have this definition in David Ley. So that's what that is. All right, so now how to. I think that's what I missed in linear algebra. I didn't understand what it was for. So then when I got into higher level classes, there was a guy that always sit with me and say, think of a matrix. This is a linear transformation. I just don't understand what you're talking about, because the way that we did it in linear algebra is we just did the procedures, row reduction, um, finding a basis. So they were all procedural. So I don't think I understood how they came together. All right, so let me show you an example. This one's quite a little bit different than just showing something is linearly independent or not. So these kind of questions come up in your book quite a bit, and they also come up in terms of ODEs, because if you, let's say you got, I got two solutions to my second order differential equation, but no, the second one is a combination of the first, or a scalar multiple of the first, because that's what it reduces down to. So you don't really have two solutions. And a second order equation should have two solutions. So it's like you come upon a solution that's not really a solution because it's redundant. And so that's what this is all about, where it's going. So here's my V1. Oh, your book uses this. I'm going to try to use what your book sees. It's 1, 2, minus 1. I think David Lay's book uses this too. So I have these three vectors. I'm really trying to encourage you not to do things manually. If I had asked you to add huge numbers together, or multiply huge numbers together, or divide huge numbers together, you would use your calculator. So your Mathematica, ChatGPT, these things are tools. Use them because they usually won't get them wrong. ChatGPT I have an issue with because sometimes it gets it wrong. That's why I'm having you learn it now. Asking the right questions and being able to use human judgment to examine it is actually important. It's a tool. And so I really encourage you to do these things on Mathematica, because, or anything, I don't care, because it's not going to get it wrong. All right, how do you do this? Well, you already know I'm lazy, so if somebody asks me, are these vectors linearly independent? What's a short, sweet way to do that?
Augment zero vector.
Yeah, but really, yeah, you can augment it with a zero vector, but that's going to have a unique solution if the determinant of the coefficient matrix is not zero, right? They only ask me that they're linearly independent. I will give you exactly the answer you were asking me. If they ask a little bit more here. They said if they're dependent, so that means I have to do more. So I will do exactly what's been asked. I don't think the soup would be happy because I'm not going to excel. This time they're asking more. So yes, this time I do have to put them into an augmented matrix. So really what you're doing this. You're setting this thing equal to the zero vector. And you're going to really be solving for C1, C2, and C3. That's what you're doing. So you're going to pop these things. What it comes down, I think somebody asked me this in the room the other day. Can I just put the coefficient matrix down since I know it's going to look like that? Sure. Human judgment. If it works and it's right and you understand where it's coming from, sure. I can recreate this from scratch if I had to. I think that's the point. Like when you skip a step, if someone asked you to fill in that blank, you could. So you know how to do it. So this is your C1 column, C2 column, and C3 column. And these are your equations. This is the first equation that's generated by setting up the vectors. You know, remember that business we did with setting the components equal to each other? I did it the down and dirty last time for this. So that's what you're going to get. And now, unfortunately, you do have to row reduce the matrix. I think what really turned me off to linear algebra in my day, when I was in linear algebra, Mathematica was just coming out. I had it at a research experience for undergrads, but I took linear algebra before that. I went to the University of Montana, one of the top 10 party schools in the nation, not really recognized for anything else. So they didn't have Mathematica. And so I really didn't know that there was something out there that could do it for me. I think once I found there was something out there that could do that for me and I don't have to worry about arithmetic, I thought I can get my PhD in math. I can actually get my PhD in math. I told Wolfram that you're the reason I went to grad school because I knew there was hope. So I hate row reducing matrices because it's really about arithmetic. And that's my point too. I'm not testing you on arithmetic. I would hope that you know, if you had to, how to add and subtract numbers and multiply numbers. You're, after all, a math major. But to actually get it perfect every single time is tough. So this is an advantage of not being in linear algebra. In this class, you get to use Mathematica. So use Mathematica or anything else. There's row reduction calculators online. And row reduce it. And this is what I get. Here's equation 1, 2, and you'll see why I labeled it 3. This is my C1, C2, and C3. I got 1, 0, 2, and 0, 1, minus 3, and a row of zeros. And I'm keeping these here so you can see the drama as it unfolds. So what's beautiful about this is it reduces it as far as it possibly can go. In your book, this is an example in your book. They did not do that. They reduced it to, they got a row of zeros and they stopped. But it wasn't reduced further, so they did the rest by hand manually. So they actually go through the whole thing manually and show you how to get everything by hand. If you're in linear algebra, they'll make you do it by hand, I think, a little bit. Hopefully not too long. If you have Dr. Allaire, he's not going to make you do that too long. Hopefully. All right, so then what do I get from that? Step 3, you got to extract your solution. For some reason, my past students never like to extract the solution back from the matrix, but that's like an important step. So what I have is 1 times C1 plus 2 times C3 is equal to 0, and 1 times C2 minus 3 times C3 is equal to 0. Notice that C3 is in both of them, common to both of them. In linear algebra, you're going to get more complicated things where maybe C2 and C3 are common to both of them. So then what you'll do is you'll look at what's common to all these equations. If you hit it on Mathematica, it's going to have row reduced as far as it possibly can go. So you know that there's no accidental, I didn't do my algebra as far as it can go, or MATLAB. So what I get from this is that C1, I put this at step 4. So notice that C3 is common to both. So what this means is that once I plug in, C is the independent variable, I can plug in a C3, and from that C1 and C2 are prescribed. So the next step is to actually write down that dependency. If you have have you guys done this already, like finding linearly independent? Right, so you probably have like the ones that he's going to choose for you are going to be like if you have a system of a 4x4, or sometimes you get like you can make a screwy system with 4x2s, like weird things, and then you'll have more than one variable in that case. Those are the interesting ones. So what that will tell you is really they're lying along the same plane, not the same line, or they're lying along a hyperplane in some other dimension. So C1 is equal to minus 2C3, and C2 is equal to 3C3, and C3 is what we call the free variable. So in linear algebra, you're going to have maybe sometimes two free variables. Two of them were like common to both. Then you'd have two free variables, and then they're going to give you a bunch of definitions of dimension of the null space. That all comes from there. Like you count the number of free variables, and they're going to tell you the dimension of the null space. Is it connecting up? The funny thing is I took differential equations too, but I feel like they were tiptoeing around all the linear algebra. We didn't actually do linear algebra. We just did characteristic equations by plugging in the R squared, like I showed you the first time. So I never made the connection. I was in a world of hurt in grad school. I'm doing this so that you have good habits in your linear algebra class. Put into vector form. If you have two free variables, you'd have to put them into vector form and then split them into pieces. So one has only like a C3 and one has only a C4, so that those will be separate. And the two vectors that you get when you factor out are going to be your basis for the null space. So then you solve, you have this C1, C2, keep forgetting they do this. C3 is really equal to minus 2C3 and 3C3, C3, which is equal to C3 times minus 2, 3, 1. C3 is free means that it just is left as C3. The third one's just C3. And now this tells you that all solutions are multiples of the vector minus 2, 3, and 1. That's what it's telling you. We were really finding the null space. That's what you were doing. This is the basis for the null space. It's just one vector. So then you know that all your solutions lie along this scalar multiple of this one vector, which is a vector. It's a vector. It's a line in 3 space. Step 6. This is what they want. They want the answer. Answer the question. They didn't ask you to do it this way. I'm asking you to do it this way. B3 is 2B1 plus minus 3B2. The reason I'm asking you to do it this way is because the whole point of it is that you're trying to find the vector as expressed as a combination of the other vectors. It's redundant. So if you found these three solutions to something, B3 is redundant. So you really only have found two. My arrows start disappearing. Are there questions? I know I'm going really fast. So I really learned my linear algebra in Hilbert spaces and linear operator theory. Not knowing my undergrad linear algebra class is like taking a boxing class at the same time as you're learning. In the other class, it was brutal. I used to just cry outside after and think like, why did I not study? That's why if I had to do it over again, I'd be an undergrad all over again, and this time I'd study. See, someone who's always perfect can't tell you that. I remember not being perfect and the cost it gave the cost. I think in calculus, you feel like everything's computational, and then linear algebra, if it's taught that way, you think, it's a little bit more the same. They tell you, here's row reducing. You do row reducing. Here's how to find a basis. Yeah. So you're never supposed to really get it, or no one forced me to get it.